So today's lesson is on inequalities. I assume that we know how to do certain things with inequalities, but you may need some help with the absolute value and some of the compound inequalities. So I just want to do a quick refresher from Algebra 2. When you solve any inequality, you have multiple answers. You're not getting something like x equals 5. I think it would help if we all use the interval notation. And you can graph them if you want as well. You know, it doesn't matter there. So the first problem here for the linear inequality is to subtract 9x from either side. So we'll get negative 6x less than or equal to 4. And what happens when we divide by a negative? I picked this problem because of that. The inequality sign flips, and this becomes negative 2/3. So if we were going to write that in interval notation or on the number line, we would have shading from negative 2/3 over to the right. So in the interval notation, we've got bracket negative 2/3 to infinity. And that's good enough if you just want to give me that answer for these problems. All right, compound inequalities is when we have two or more inequalities at the same time. So here, just make sure when you're solving, you add 5 to all three regions. So we're going to add 5 here, here, and here. Okay, and then same thing goes for the 2. We're going to divide everything by 2. So we end up getting x is between 5 and 7. Now again, if we were shading that on the number line, our shading would be in between our two, what I call boundary points. Here, again, they are open circles at 5 and 7 because the inequality symbol is less than. So we have open brackets or parentheses for our interval notation. Okay, so just a little refresher on linear inequalities. Today we're going to focus on solving and graphing nonlinear inequalities, primarily quadratics and rational. Now this is a quick lesson. We're covering a lot of things here at one time. So with the quadratic inequality, the first thing to note is that your quadratic is to one side of the inequality. Make sure it's either on the left side or the right side. It doesn't matter which one. Okay. Now if you wanted to graph this on the graphing calculator, now and I'm going to pull up the calculator. It takes a little while to load. And we'll just do this first one. In the flex book you have the little demonstration about how what you're looking for visually when you are doing inequalities. Doing inequalities on the graphing calculator is a lot easier than doing them algebraically. Now I want you to know how to do them algebraically, but we'll take a look here as well. Okay, so if we just go ahead and just plug in the quadratic, which was x squared minus 5x plus 6, and then graph that, you can see, this is not the greatest example. I'm going to zoom in a little bit here. Primarily what we're looking for here is where the quadratic falls below the x-axis, okay? And it's only in a little tiny region here between here and here, okay? So what we want to do, let me drag this over to the smartboard, okay? To verify what my answers are, what my x-intercepts are, how do we get x-intercepts for quadratics? We would set it equal to 0 and solve for x. So let's factor this. This will factor to x minus 3 times x minus 2. Okay? Now we can't just say, this is still less than or equal to 0. We can't say our answers are 3 and 2 and maybe shading in between or shading on the outside. How do we know? The algebraic way is to set up what I call boundary points. So x equals 3 and x equals 2 are what are known as boundary points or your x-intercepts from the graph. So this in fact here was 2 and this was 3. Okay? Now algebraically on the number line what we want to do is test the intervals in which these boundary points fall. So I'm going to put 2 here and 3 here. Okay? Clearly from the graph we can see that the quadratic falls below the x-axis or less than or equal to 0, okay, between 2 and 3. So let's verify that now. to do the checking, and on the Flexbook that I created for you, you can see some examples both graphically and algebraically, okay? So they set up a little table. I'm just going to do a quick demo here on the number line. What we want to do, we have 3 regions here, to the left of 2, in between 2 and 3, and to the right of 3. So we're going to test values in each of those regions. So if we test values to the left of 2, let's say let x equal 0, okay? We end up getting 6 is less than or equal to 0. Well, that's not true. We don't fill in that area there. In between, let's pick x equals 2.5. I'm going to substitute it into the factored form to make it easier. I just need to know what the sign is. I don't really need to know the value. So 2.5 minus 3 will give me a negative value, and 2.5 minus 2 will give me a positive value. And a positive times a negative is negative or less than 0. So I'm going to shade in between 2 and 3. If I pick, say, 4 to the right of 3, again, I'm going to get here a positive times a positive. And that is not going to be less than or equal to 0, so we don't shade that area. The last thing, just to double check, is those open circles and closed circles. At both 2 and 3, we have closed intervals because the symbol is less than or equal to 0. So when I'm giving my answer in interval notation, we'll say that the solution is bracket 2, 3 bracket, and that means all values between 2 and 3. Okay? All right, let's try the next one. The next quadratic has x squared plus 2x on one side and 3 on the other. So just make sure we move the 3 to the left. Okay, I'm not going to graph this one on the calculator. Let's factor this. You can always just graph on the calculator to verify your answers at the end, if you want, okay? So we've got x plus 3, x minus 1 is greater than 0. So my boundary points, I call them boundary points, for this problem are going to be x equals negative 3 and positive 1. So on my number line, let's put negative 3 and 1 there. They will be open intervals because the symbol is just greater than. And if I want to do my quick check here, to the left of 3, let's pick negative 4. So again, I'm going to fill into the factored form, and that will give me a negative times a negative. And a negative times a negative is positive. I'm going to shade that. Between negative 3 and 1 would be 0. Always pick 0 whenever you can. And that gives you negative 3 is greater than 0. Clearly that's not correct. And then to the right of 1, let's say x is 2. 2 plus 3 is a positive value, and 2 minus 1 is a positive value. So a positive times a positive is going to be greater than 0, and we shade on the outside of 1. Solution set for this problem will look as follows in interval notation. Negative infinity to negative 3, union, or, remember we use the word or with union, positive 1 to infinity. Okay? All right, so those are 2 examples of quadratics. If you, again, refer back to the Flexbook, you can see other examples, further examples if you need some more. All right, rational inequalities is a little bit different. Again, we can graph that on the calculator and see where that is falling above and below the x-axis to verify. Sometimes those graphs get a little bit more complex to see, and we do have to zoom in a bit on those. Okay, so first thing, to find our boundary points for the rational inequalities, if it's already simplified, I'm trying to stick with just basic ones in this lesson for you guys. What we want to do is set my numerator equal to 0, so x minus 3 will give us x equals 3 as the boundary point. But we also have to consider limitations on the domain, okay? According to my denominator, if this rational expression existed, x plus 1 cannot equal 0. So we have to also remember that x cannot equal negative 1. That is included in the boundary points as well. So to get the normal boundary point, you set your numerator equal to 0 and solve, but also include restrictions on the domain. Okay? So now we've got -1. I feel like we just did -1 and 3. I think we did -3 and 1. That's fine. -1 and 3 are our boundary points. They are both closed intervals. And we'll do the same thing, check each region. So when I substitute a value into the left of -1, we got, what do you want to pick there? -2, okay? If we pick -2, we're going to get a negative divided by a negative. And a negative divided by a negative is going to give us a positive value. We shade that. I'm not so concerned with what the value is. We're just checking it. When I check 0, okay, I get -3, and -3 is not greater than 3 equal to 0, so I don't shade that area. And when I pick a value to the right, say 4, again, here I'm going to get a positive over a positive, and that is greater than or equal to 0. So the shading goes to the right there. Okay? Now, one thing we have to be careful of. Because I stated over here that x cannot equal -1 at all, I should not have a closed interval at -1, should I? If it can't equal -1, then we have to open that interval up. So in the quadratics, we went primarily by the greater than or equal to, less than or equal to symbol to determine the open and closed regions. But with the rational inequalities, we have to double check that domain feature, okay? So please just make sure that that's a little bit tricky here. So my final solution then would be all values that go from -infinity to -1, open, or we have values that go from 3 to +infinity, okay? All right, last example for this unit right here involves a rational inequality that's not simplified. Now, what we need to do here is actually move the 2 over to the right. This is one thing that we can do. And if you don't like it written that way, if we want to move the x plus 1 over x minus 3 would be less than -2, and then bring the 2 over, that's fine. Okay, and 2 less than 0. What we can't do really is multiply both sides by x minus 3 right away because we don't know whether that value is positive or negative. So this is the better thing to do, and that's to move the 2 over and then get a common denominator and simplify it. Okay? So just multiply the 2 by x minus 3. Let's practice some of our rational simplification. And then up top, we're going to end up with x plus 1 plus 2x minus 6 all over x minus 3. And then that will lead us to 3x minus 5 over x minus 3. Okay? And that's going to be less than 0. All right, so my boundary points here are going to be +3. But at +3, it will be open because we can't have this rational function defined if we have 3 as a root. And then we've got, what is that, 5/3. We can just write that kind of close to that, and that's going to be closed. Okay? And then we go through the same process and check our points and our regions. So let's pick, we can pick 0 over here. When we plug in a 0, we get a negative over a negative, which is not negative, so we don't include that. A good point to pick between 5/3 and 3 might be 2 to make it a little easier for us. So we'll get 6, which would be 1 over -2, and that is less than 2. We'll shade in between. And then to the right of 3, if we pick 4, we'll get a positive over a positive once again, which is not negative. So this final solution would be closed at 5/3 to 3, open, solution set 4. That last one. Okay, I'm going to stop this video. I'm going to do the second one for the absolute values. That should only run us about 10 minutes.